你做几多个啊？哦。actually 这个很 OK，我3015哦。fuck up。你做3015哦，那个是 fuck up 的。我是那边一直 OK 哦，那个per unit 我还 OK。一来到那个什么，你说那这个 square 哇，太规矩，真是太多了。超恶心，他的 note 是他一篇的话呢，我这么清楚 ？Double.
I know. How can you finish?
Sekali ada have tutorial sheet.
Check.
我没有带。
这个是你的，看那个扫地的。这个是。
Okay, so today we will look at transformers. Okay, so this figure here, okay, this magnetic circuit here is a simple transformer. Okay, you have a magnetic core and you have two windings, okay, one on each side of the core. Okay, the one on the left, okay, the coil on the left has N1 number of turns, okay, and has a current I1. Okay, this coil is called the primary side coil. Okay, and the one on the right has N2 number of turns and carries a current I2. Okay, this one is called the secondary side. Okay, now when an input is connected to the primary side, okay, the input voltage is V1. Okay, a current I1 flows in the circuit. Okay, this I1 multiplied N1 establishes a MMF. Okay, the MMF will produce a flux flowing in the magnetic core. Okay, if the input voltage is AC, then your flux will also be AC. Okay, this flux travels through both the primary side coil and the secondary side coil. Okay, so since the flux is AC, okay, there will be a voltage induced in the primary side coil, okay, given by E1. Okay, that voltage is given by L di1 dt or N1 d5 dt. Okay, they're the same thing. Okay, now if the flux is sinusoidal, okay, where phi is okay, the flux is sinusoidal, which should ideally happen. Okay, the magnitude of the voltage E1 will be given as 4.44 times N1 is N1 times the flux. Okay, the maximum flux multiplied by the frequency of the input. Okay, right, this 4.44 is actually 2 pi divided by square root 2. Okay, now since the flux is AC, when the flux goes through the secondary side coil, the coil sees a time varying flux. So according to Faraday's law, there will be a voltage induced in the secondary side coil as well. The magnitude of the voltage is given by E2, and by Faraday's law it's also equals to N2 d phi dt. Okay, so by the same logic, the flux is sinusoidal. Okay, E2 will be 4.44 times N2 times 5 times F. Okay, now this one is an ideal transformer. Okay, so the coils have no resistances. Therefore, V1 will equal to E1, and V2 will equal to E2. Okay, now the schematic for the ideal transformer is given by this. Okay, so this one is the primary side, this one is the secondary side. Okay, A is the turns ratio given by N1 over N2. Now this dot convention here, you see, okay, the dot, right, is always such that, okay, on the primary side, okay, the dot points to the positive voltage terminal. Then on the secondary side, the voltage will also be positive at the dot. Okay, and for the current, on the primary side, if the current flows into the dot, on the secondary side, the current flow out. Okay, so that's the dot convention. Okay, so if it was like this, then the current will be, the voltage will be like this. Okay. Okay, so if you take the ratio of E1 over E2, you get N1 over N2, and that's the turns ratio A. Now the apparent power is an ideal transformer. So the input power E1 I1 must equal to output power E2 I2. Okay, so when you rearrange, I2 over I1 will be E1 over E2, and that will be A. Okay, or N1 over N2. Okay. Okay, any questions? Okay, obtaining the ideal transformer? No. Okay. So we look at the first question. Okay. You have a single phase 1 kVA 60 Hz transformer. Okay. Has 120 turns on the primary, and you're supposed to calculate the turns ratio. Okay, so the information given to us is S is 1 kVA. That's the rating, power rating. Okay, apparent power. Okay, we are also given E1 equals to 250. E2 is 100. And F is 60. So calculate the turns ratio. So we use this E1 over E2 equals to Okay, so turns ratio is E1 over E2. Okay, so E1 is 250. Okay, given the question, that's the rated value. Okay, when you have 250 volts in the primary, you will get 100 on the secondary side. So 250 divided by 100, so it's 2.5. For the second one, the number of turns on the secondary winding. So N1 over N2 is the turns ratio. N1 is 120. Okay, so N2 will be 48. Okay, part C, the rated currents of the two windings. So you get rated current when you have rated voltage and rated power. Okay, so S is E1 I1. So I1 will be S is 1000 divided by 250, so that's 4. And I2 over I1 is A. Okay, so I2 will be A, which is 2.5 multiplied by 4. Okay, so that's 10. Or conversely, you could use S equals to E2 I2. You'll end up with the same thing. Okay. Okay. So for part D, okay. So supposed to find the maximum flux in the core when the transformer is connected to a 250 volts 60 hertz source. Okay, so if E1 is 250 and F is 60, so if E1 given by the equation there, you're supposed to find phi flux. So it's 4.44 times N1 times phi max actually times F. So that's 250. So the flux will be right. Okay. Now, if the supply was changed to 220 50 hertz, so that means now E1 is 220 and the frequency is 50. Okay, so you have okay. Right? Okay, so when the input voltage is changed to 220 and the frequency is changed to 50, your flux will change to 8.26 milliwebers. Okay, the question asks to find the percentage change in the flux density. Okay, so what they're asking is this one. Okay, the change in the flux. Okay, so the change will be the new flux divided minus the old flux divided by the old flux. Right? Okay. Okay, any questions? No questions? Okay. Okay, so that was the ideal transformer. Okay, unfortunately, practical transformers are not ideal. Okay, practical transformers differ from ideal transformers. Okay, because practical transformers, okay, these two windings are conductors. Okay, all conductors have finite resistances. That's one. Second is, okay, not all the flux, okay, that's produced by the primary side coil goes through the secondary. In other words, there will be some flux that will actually escape through air. Okay, so let's say that, okay, this is the flux that couples the primary side to the secondary side. Okay, in addition to this, there will be flux, okay, that only links the primary side coil. Okay. Right? Okay, and the same thing happens for the secondary as well. Okay. So the resistances of the coil, okay, can be taken into account, okay, by just modeling those resistances by a resistor. Okay. We call it R1. R2. Okay. So we still have the ideal transformer, okay, but with all those non-idealities taken into account. Okay, so the resistances of the coil, okay, in a practical transformer is modeled as winding resistor, okay, on the primary side R1, on the secondary side is R2. Okay. Now for this leakage flux, okay, is modeled as an inductor. Okay, L1, I think, right, JX2. Better, because it's AC. Okay. Okay. Now, in an ideal transformer, okay, the core is assumed to have a very high permeability, so its reluctance is assumed to be 0. Okay, but in a practical transformer, that's not the case. Okay, the core will have a finite permeability and therefore a finite reluctance. Okay, so once there's reluctance in the magnetic circuit, okay, the core will have a finite inductance value. Okay, so the inductance is modeled as, okay, an inductor in parallel with the ideal transformer on the primary side. Okay, JXM. Okay, XM is the magnetizing reactance. Okay, now the last one, okay, is, okay, in a practical transformer there will be losses. Okay, electrical losses, okay, due to hysteresis and eddy current. Eddy current. Okay, so these two losses are modeled as a resistor. Okay, in parallel with XM. Okay, it's called RC. Okay, RC is the core loss resistance. Okay, now why is it like that? Okay, it's supposed to be covered in the lectures. Okay, I don't have the time to cover it here. Okay, I just tell you that this, okay, is done like this. Okay, and this is the circuit for the practical transformer. Okay, so you have the ideal transformer. Okay, still the ideal transformer, everything in blue is ideal. Okay, and all the non-idealities, okay, are shown in red. Okay, V1 is the input voltage. Okay, V2 is your output voltage. Okay, I2 is your output current. I1 is now the primary side current. Okay, so this one will be called, if I call this I1, then this one will be IP. Okay. Right. Okay. So that's the circuit for the practical transformer. Okay. Now it's not convenient to have this blue color ideal transformer here. Okay, so what is usually done is this ideal transformer is removed. Okay, and everything on the secondary side will be moved to the primary side, or everything on the primary side will be moved to the secondary side. So we take it 4.2. Okay, you're supposed to refer everything to the low voltage side. Okay, so for this question, I will bring everything from the primary side to the secondary side. Okay, so when I remove the ideal transformer, okay, then I bring everything from here to here. Okay, everything on the right hand side, the secondary side stays the same. Okay, nothing changes. If I take that away, I'll have okay. Okay, so I remove the ideal transformer, everything is brought to here. Okay, and you see all the values now will have a prime. Okay, superscript prime. Okay, okay, to denote that now we have the primary side reflected onto the secondary side. Okay, now the values of this prime, right, R1, okay, can be shown to be R1 over A squared. Okay, where A is the turns ratio. Okay, X1, the same thing, is okay, right? Okay, it can be shown to be all these values. Okay. Okay, the derivation should be covered in the lecture, sir. Okay. Okay, so now for question 4.2. Okay, we have 100 kVA, okay, 11,000, 2,200 volt, 60 hertz transformer. Okay, so we are supposed to calculate the full load rated currents on the high voltage and the low voltage sides. So we are supposed to find I1 and I2, okay, of the transformer. Okay, or this one. Okay, I1 and I2. So we have S equals to Okay, so for the first part, okay, no change, okay. I just replace E1 with V1, that's all, okay. So everything else the same. The turns ratio is E1 over E2, that's 5. Okay, S is the rated power, the voltage multiplied by the current. Okay. So the primary side current I1 is 9.09. Secondary side is just A times I1. Okay, just refer to the previous question. Okay, AI1, so that's 45.45. Okay. So now for the second one, okay, the transformer has the following parameters. Okay. Then you have to draw the exact equivalence circuit. Okay, refer to the low voltage side. So the exact equivalence circuit is this one. Okay, with the proper numerical values. Okay, so I'll just do it here. Okay, so we'll do R2 first. So R2 is, okay, on my diagram, R1 is their RHV, okay, R2 is RLV, okay. So all the ones, right, on my diagram is the HV for them, for the question, and the 2 is the LV, okay. 1 is the primary side, which is the high voltage side, okay. Primary is 11,000 volts, secondary is 2,200. So the primary is high voltage and the secondary is low voltage. Okay, so the R1, the subscript 1 is the high voltage side, and subscript 2 is the low voltage side. So take R2 is X2 is 2 pi F L2. So that is okay. Okay, anyone don't understand how I got the numbers? Anyone who understand how I got those numbers? Okay, so you're supposed to calculate the input voltage and input current when the transformer delivers rated load at 0.85 power factor lagging and rated voltage. Okay, so there's a lot of information there. Okay, you are supposed to calculate the input voltage and input current. So basically it's V1 and I1. Given that the transformer delivers rated load, okay, so load means at the output side. Okay, rated load means rated power. Okay, so therefore the output power here, S, apparent power is 100 kVA at 0.85 power factor lagging at rated voltage. So rated voltage V2 means 2200. Okay, so that's how you interpret the information. Okay, so it's an AC circuit, so everything is AC. Yeah? So you have to use your phasors to do it. Okay, so V2 is okay. Okay, I put 0 as the reference. Okay, 0 just means it's the reference. Okay, we want to find V1. Okay, so we find V1 on this circuit. Okay, or V1 prime on this circuit. V1 prime, I1 prime. Okay, given V2 and given the power, we can find I2. So we need to find V1 prime. Okay, now this is just AC circuit analysis. Okay, there are a few ways to do it. Okay, the approach that I would take is, okay, I'll find this intermediate voltage first, called E1 prime. Okay, then from E1 prime I'll find V1 prime. Okay, E1 prime is just this drop plus V2. Then V1 prime will be this drop plus E1 prime. Okay, so that's how I'll do it. Okay, so now we are given the power. S is 100 kVA. So I2, okay, is given by S divided by V2, okay, at an angle of negative inverse cos power factor. Okay, I hope you all know this. Okay, the magnitude of I2 will be S divided by V2. Okay, the angle will come from the power factor. Okay, if the voltage has an angle of 0 and the power factor is lagging, the current angle will be negative. Okay, and the value of the angle will be the inverse cos of the power factor. So I hope you all know all these. Okay, if you are not aware of this, you have to go back and read it. Okay. Okay, so E1 prime is V2, okay, KVL, okay, V2 plus I2 times this impedance drop. Okay, so you just put in the values together with the angles. Okay, the angles must all go in, and there's a J. Okay, the angles must go in. Without the angles, you get the wrong answer. Okay, so the angles must all be there. Okay, and then you should get this value. Okay, then now E1 prime, or sorry, V1 prime will be I1 prime times R1 prime plus JX1 prime plus E1 prime. Okay, but we need to find what's I1 prime. I1 prime is just I2, okay, plus whatever current flows through here. The current that flows through here is called the no load current. Okay. Okay, so the no load current is this current, which is E1 divided by RC, and plus this current E1 divided by JXM. Okay, so that's what I have here. So it should be 1 point. Okay, then I1 will be okay, right? Okay, so V1 prime will be E1 prime plus I1 prime R1 plus JX1. Okay, again that's KVL. Okay, so you end up with this answer. Okay, and the input current I1 prime is this one, no load current plus this current. Okay, that's KCL. Okay, so you end up with this. Now the question asks us to find the voltage, the input voltage and input current. Okay, so input voltage is V1, input current is I1. Okay, what we have calculated is V1 prime, I1 prime. Okay, or V1 reflected to the secondary, I1 reflected to the secondary. So now we need to reflect this back to the primary to give us the actual value V1 and I1. Okay, so just now on the board I wrote V1 equals to A times V1 prime. Okay, that was what I wrote on the board earlier. Okay, you all can check back, that's what I wrote. Okay, so A is 5, so you just multiply this by 5. So you should get okay, and for the current, okay, I1 equals to I1 prime over A. Okay, when the question says find the voltage and current, they usually want the magnitude only. The angle is not so important. Okay, so just the magnitude that counts. Okay. Okay, so any questions? Any questions? Any questions? You're all comfortable with AC circuit analysis, hopefully. Okay, so just now, okay, we reflected everything from the primary side to the secondary side. Okay, so now, now we can do the opposite as well. Okay, so we bring everything from the secondary side to the primary side. Okay, so when that happens, you have So you end up with this equivalent circuit. Everything on the primary side, okay, stays the same, nothing changed. Okay, on the secondary side, you just copy everything over, okay, and you put the superscript prime, okay, on all the secondary side quantities, meaning R2, X2, I2, and V2. Okay. So if just now R1 prime, okay, earlier on R1 prime, okay, R1 prime was R1 over A squared, right? The primary side resistance, okay, referred to the secondary side is the actual resistance divided by A squared. Okay, so now if you do the opposite, you bring everything from the secondary side to the primary side, will be okay, you'll get the opposite. Okay, opposite relationship. Okay, x2 prime will be okay. Alright, that's what you get. Okay, now okay, this we saw earlier, okay, from that, okay, from question 4.2. Okay, this circuit is quite complicated. Okay, you want to find the input voltage given the output voltage, you have to find the intermediate voltage first. Okay, so usually, okay, this circuit, which is the exact equivalent circuit of the transformer, okay, can be simplified one step further. Okay, now usually R1 plus JX1, okay, this winding resistance and the leakage reactance, okay, is usually much smaller compared to RC and XM. Okay, the core loss resistance and the magnetizing reactance. Okay, that's usually the case. Okay, in a properly designed transformer. Okay, so when that holds, okay, we can shift this branch, okay, RC in parallel with JXM to the left. Okay, without introducing much error. Okay, so if you do that, you will end up with okay, so you end up with this. Okay, so if I bring this over here, okay, this R1 plus JX1 will be in series with R2 plus JX2. Okay, they will be in series. So I combine them. Okay, I'll call it RE1 plus JXE1. Okay, E means equivalent. Okay, so RE1 will be right? Okay, everyone okay? From here to here. I just move this here. Okay.
So, is it always to the left? If let's say we refer to the secondary side,
It's also to the left.
it's also
Yeah, it's also to the left. Yeah. Okay, any other questions? No, okay, so we can continue. Okay, so we are going to use this circuit, okay, to do question 4.3. Okay, so the approximate equivalent circuit referred to the high voltage side is that one. Okay, over there, that's 4.3A. Yeah? Okay, and we are supposed to calculate the no load current, no load power factor, no load power loss, and full load copper loss. Okay, and part B, calculate the input voltage and input current. Okay. Okay, so okay, the values are still the same. S is 100, EA, E1 is 7. Right. Okay, so RC is okay. So okay, this one is from the question, okay, and this one is derived from the parameters given in the question also. Okay, so RC is 125 kilo ohms, XM is 2 pi FLM. Okay, so that is 60.32 kilo ohms. Okay, RE1 is R1 plus A squared R2. R1 is 6 and R2 is RLV, right? So that's 0.28. Okay, so that's 13. XE1 is X1 plus A squared X2. Okay. Okay. A squared X2. Okay, so that's 2 pi F L1 plus A squared L2. Okay, they're the same thing. So given in the question, L1 is LHV, which is 0.08, and LV, low voltage, is 0.0032. So that's 60.32 ohms. Okay. Right, so now we are supposed to find the no load current. Okay, no load current is the current that flows through here. Okay, given that the output is open circuit, okay, no load connected to the output side. Okay, so when there's no load connected to the output side, I2 is 0. So we only have this. Okay, so if we take V1 to be, okay, we take this, okay, then INL will be V1 over RC plus V1 over AXN. Okay. Okay, and the no load power factor would be, power factor at no load would be cos angle of the voltage minus the angle of the current. Okay. Okay, part 2, the core losses. Core losses is the power dissipated by the core loss resistance RC. Okay, so that would be PC equals to V1 squared divided by RC. Okay, so that's okay, the full load copper losses. Okay, so the full load current, okay, the full load current we calculated in part 4.2a. Okay, so from Okay. Right, okay, from 4.2A we calculated IA, I2 is 5.45 amperes. So I1 or I2 prime right. Okay, so the full load copper losses is the power dissipated by RE1. Okay, those are the copper losses, right? These are the winding resistances. Okay, R1 and R2. Okay, so copper loss refers to this. So the full load copper losses will be PCU will be I2 squared, I2 prime squared times R squared. Okay. Okay, and the last one, part B, you are supposed to use the approximate equivalent circuit, okay, to calculate the input voltage and input current for supplying full load at 0.85 power factor lagging at rated voltage. Okay, so that's basically the same as 4.2B. Okay, we have this. Okay, so follow the same steps as 4.2B. So we take V2 prime. Okay. Right, V2 prime is AV2. Okay, magnitude wise. I know. Okay, the extra is making noise. Okay, so okay, the steps are the same. Okay, so there's the KVL. Okay, this is the magnitude of the voltage, and the input current will be INL plus I2 prime. Okay, where INL is this one. Okay.